So we've talked about vertical asymptotes, and now we want to talk about horizontal asymptotes. Unfortunately, this is going to require a type of limit that we haven't seen yet. Specifically, we're going to talk about the limit at infinity. We say that the limit of a function f at infinity, which we write as the limit as x goes to infinity of the function f of x, is L, meaning we say this is true when as we put in larger and larger values of x, so x values that are can't really say closer and closer to infinity, but just get really, really big, the values of the function are getting closer and closer to this number L, whatever L actually is. Similarly, we can talk about limits at negative infinity. So we could actually say this is the limit at positive infinity if we need to be specific. But we can talk about the limit as x goes to negative infinity of the function equaling L. This means as we put in larger negative values, so big numbers that are negative, into our function, we get closer and closer to this limit of L. It's also possible to talk about limits that are not necessarily a finite number L. We could have a limit as x goes to infinity of f going to infinity. Think about x squared here. If we put in bigger and bigger values of x, we get bigger and bigger values of our function, and there's no bound on that, on how big it can get. It can get bigger and bigger and bigger. Or we could even look at a function where as x goes to infinity, we get closer, well, not closer and closer, but we get really big negative numbers. So it just keeps decreasing down to negative infinity. This could be something like negative x squared, or something like that. These are all possible things we can get. And we can see them on the other side as well. So x goes to negative infinity of a function, it could go to positive infinity, or it could go to negative infinity. The book doesn't really talk about these versions and just kind of focuses on these, but it is kind of useful to just realize that we can talk about limits at infinity that are infinite. These aren't really completely separate from what we were talking about with regular limits. Now, one useful thing about limits at infinity is that most of our rules for limits actually still work. If I have the sum of two functions and I can take the limit of each part separately, then the sum of those two functions will go to the sum of the limits. We could write something like the limit of f of x being L at infinity, and the limit as x goes to infinity of g of x equals m means that the limit as x goes to infinity of f of x plus g of x is going to be L plus m. So we can go ahead and think about things term by term. We have to be careful if one of our limits turns out to be infinity, but as long as we don't have something like that, we can go ahead and just add our limits together. Or if these were subtracted, we could subtract the limits. Or if they're multiplied, we could multiply the limits. All those normal rules of limits still work if we're taking the limit at infinity rather than the limit at some number x equals c. And that's going to be very useful for us in evaluating a lot of these limits. Now, it is still tricky to evaluate limits at infinity right away, because unlike with, say, the limit as x goes to 1, we can't just plug in a number. If we were trying to say x squared as x goes to 1, we could just plug in 1 and get our answer right there. We can't do that at infinity. We cannot plug in infinity. It's not a number to be plugged in. So instead, we actually look at a particular example that'll be very helpful for us. Specifically, what happens to a power of x as x goes to infinity? What happens to x to the r power? Now, there's different cases here. This doesn't always work the same way. If, say, r is 2, then we're looking at x squared as x goes to infinity. We're definitely going to get infinity in that case. However, if r is -1, now we're looking at 1 over x. And if we remember what 1 over x does, it does something like this. This is the graph of y equals 1 over x. In other words, x to the -1 power. As we let x go off to infinity, this is going to get closer and closer to 0 as we go. So it really comes down to 3 different cases. If r is positive, then we're looking at, say, like x squared, x cubed. All of those, we actually end up getting bigger values of our power than we had putting in the x. And if x is already going to infinity, well, that power has to go to infinity. If r is negative, we actually end up in a similar situation as 1 over x. We're going to go to 0. So 1 over x, 1 over x squared, 1 over x cubed, all those end up going to 0 as x goes to infinity. Finally, we have the edge case of r equals 1. R equals 0. In that case, the limit actually is 1. And that's just because x to the 0th power, anything to the 0th power other than 0 itself, is always equal to 1. X to the 0th power is 1. Pretty much by definition. So as if we only are working with 1, and we let x go to infinity, it's still going to stay at 1. Now things become a little bit more complicated if we go to negative infinity instead. We're still going to have a similar kind of breakdown. If r here is negative, we're going to go to 0. If r equals 0, we're going to go to 1. But if r is positive, this could go to either positive infinity or negative infinity. Think about, say, x squared. If we look at x squared, remember our graph of this one looks something like this. As we go off to negative infinity, we do get positive values. It continues to go to positive infinity. On the other hand, if we look at x cubed, now our graph looks something like this. In this case, we definitely do go to positive infinity as x goes to infinity, but as x goes to negative infinity, we're going to go to negative infinity. We're still going to get an infinite value. It's just going to be negative instead of positive. To put my function here. Finally, there's a even more complicated wrinkle to this. What about something like x to the 1/2 power? Remember, that is the square root of x. The graph of this one looks something like this. Notice it doesn't have anything for negative values, for negative values of x. We definitely can't even talk about the limit as x goes to negative infinity, because this doesn't even have numbers in the negatives to even go to. So these formulas are only going to work. Oops, let me change it back to this. As long as x to the r is defined for negatives. So if x to the r is not defined for negative values, usually that's when r is a fraction with an even denominator, something like 1/2 or 3/4 or something like that, where we end up with these even roots. In those cases, we have to kind of just say, well, we don't have a limit, because it doesn't make any sense to even talk about a limit in that case. So definitely a little bit more complicated than the positive infinity case, but it does give us an idea of what's going on. And that idea is really going to be the key for us to actually do stuff. But we're going to focus mostly on limits to positive infinity because of that fact. Just to kind of avoid those extra little complications that kind of get in the way. So actually, let's go ahead and take some limits at infinity. We're going to look at problem 44. This actually has 3 parts to it. We're going to take the limit as x goes to infinity of 4 minus 5x over 2x cubed plus 6. What happens to this function as x goes to infinity? That's not a very clear question. If we put bigger and bigger values of x into the numerator, we're going to get numbers that are probably pretty close to, they're going to negative infinity, because the 4 doesn't really change much, but then we have a negative 5 times whatever we had here. That part's going to grow really, really big and overwhelm the 4. We're going to go off to negative infinity on top. On the bottom, well, the x cubed is going to go to positive infinity, times 2 is still going to go to positive infinity, and adding 6 to that is actually just going to make it even slightly bigger. So the bottom is going to go to infinity as well. Negative infinity over infinity, well, maybe the infinities cancel out. Maybe they don't. We're not entirely sure. So we have to be a little bit more careful than that. Now, when it comes to a rational function like this, there's one big trick that's very useful. We're going to multiply, well, let me just rewrite it out, and then we'll modify it a little bit. We're going to do a little bit of algebra here. I'm going to multiply the top and the bottom by 1 over the biggest power on the bottom. So the biggest power on the bottom is x cubed. Essentially, I'm going to divide the top and bottom by x cubed. Remember, I do need to distribute that to each of our terms. So 1 over x cubed times 4, which is just 4 over x cubed. 1 over x cubed times 5x, well, that's going to cancel out the x here and leave us with a 2 on the bottom. So we're going to have a minus 5 over x squared. On the bottom, we have 2x cubed divided by x cubed. The x cubes cancel out. We just get a regular 2. And finally, the 6 times the 1 over x cubed is 6 over x cubed. Now, that looks a lot more complicated than what we started with. But there's something very important here. The fact is that each of these terms is now a number times some power of x. And specifically a power of x, something like this, where the r is a negative or equal to 0. We're not going to be dealing with any places where the r is positive, because so we don't have to worry about infinities here. 4 times x, we should say this 4 over x cubed, but it's 4 times x to the negative 3. That term, as x goes to infinity, is going to 0. So we get a 0 for that term. This term is also going to 0. The 2, well, 2 is just going to 2. Technically, this is 2 times x to the 0th power, if you really want to put it that way. But the x to the 0th power is going to 1. So we just end up with a 2 there. And finally, the 6 over x cubed is also going to 0. So we don't have to worry about infinities in this anymore. Well, the bottom is going to 2. The top is going to 0. So overall, this is going to 0. This limit is 0. We're going to do kind of the same thing on b. In fact, b is actually going to look very similar. It's going to be 4 minus 5x. So the same numerator. The denominator here is going to be 2x plus 6. We don't have the cube this time. But we do the same kind of thing. We divide the top and bottom by the biggest power on the bottom. This time it's just we're going to divide by x. Maybe, let's go ahead and even just put that in here right now. If I divide each of the terms on top by x, I have 4 over x minus 5. This time we don't have 5 over something. It's just 5. The 2x divided by x is going to be 2. And we're going to have a plus 6 over x. And this time, the 4 over x goes to 0 for the same reasons that we had before. The 5 stays a 5. We have a negative 5 here. The 2 stays as it is. And the 6 over x becomes a 0. In other words, we actually do have a non-zero limit of negative 5 halves. Finally, part C. Again, this is a very similar looking function. This time we're going to have a 4 minus 5x squared over a 2x plus 6. So instead of having a cube on the bottom like we had in the first one, now we have a square on top. We're still going to do the same kind of thing. I'm still going to multiply the top and bottom by 1 over x, because x is the biggest power on the bottom. If I distribute that, we have a 4 over x. Here we have a minus 5x squared divided by x. That will cancel out one of the x's. We're actually still going to have an x on top this time. The 2x becomes just a 2 when we divide by x. And finally, we're going to have a 6 over x. As we let x go to infinity, this part goes to 0. The 2 stays the same. The 6 over x also goes to 0. But negative 5x, as x goes to infinity, is going to minus infinity. So we actually did have an infinity in this computation. Technically here, you want to be a little bit careful about actually writing infinity as if it were a number. That's kind of cheating our notation a little bit, but it's not a problem in this particular case, because all we end up doing is subtracting it from zero. The zero is not going to have any effect on infinity, and then we're going to divide it by 2, which half of infinity is still infinity. We're still getting unboundedly big numbers, or I guess unboundedly small numbers if we take the negative into account. But the point here is we get a negative infinity for our limit. Now, I think the book actually wants you to say that the limit doesn't exist in this particular case, which is technically true. We don't consider negative infinity or positive infinity as actually being numbers that are limits of the function. They're just useful shorthands to tell us what the function is doing. But the reason I want to caution you about treating infinity or negative infinity as actual numbers, in situations where we have certain kind of forms, we have problems. For instance, we can't take infinity minus infinity. This doesn't really immediately mean anything. We'd actually have to investigate more carefully what's going on in these situations. Same thing with an infinity divided by an infinity, or one of those could be a positive and one of them a negative, or both could be negative. In that particular case, we have more to do. We have to think more about it. And even a case like 0 times either one of the infinities. Here, it doesn't immediately mean 0. It doesn't immediately mean infinity. All these are what we call indeterminate forms. If we run into one of these, we actually have to take a step back and try something different. But in this particular case, we did not get an indeterminate form, so it wasn't a problem. I should also mention that we've already seen an indeterminate form before. Specifically, 0 over 0 was a particular one that we had to pay attention to before. In fact, anytime we use the limit definition for derivative, we were seeing that kind of thing. And so, because we were always getting 0 over 0, we had to try something different. So, anytime when you're taking a limit and you run into any one of these forms, you have to stop, take a step back, and try something else, because these forms don't tell you anything. Getting a little bit off of what the book wants us to do, though, so let's get a little bit more on topic. What we're going to do is actually go back and talk about horizontal asymptotes. Function f has a horizontal asymptote. So I'm going to abbreviate, but I'll just keep. Yeah. It has a horizontal asymptote of y equals L if either the limit of f at infinity, should say either of the limits. That's what's tripping up. Either of the limits of f at infinity or negative infinity is L. Basically, if we take the limit of f to either side and we get a finite value of L, then we have a horizontal asymptote at L. In the case of a rational function, like we had in the last problem, problem 44, all these were particularly important kinds of functions. They're all a polynomial divided by another polynomial. That's what we call a rational function. So some function of the form f of x is p of x over q of x for polynomials p and q. That's what we call a rational function. And in those situations, we can do exactly the same techniques that we applied to problem 44 to get some general rules. In fact, we're just going to go ahead and use these rules in most of our problems. These rules involve comparing the degree of the numerator versus the degree of the denominator. Because what the key points were here when I divided by the highest power on top and bottom was what powers were left on the other one. So if I say have a higher power on the bottom, when I divide the top by that higher power, I was left with only fractions on top that had x's on the bottom, and those end up going to 0. In fact, all of our terms on top ended up going to 0, and we got 0 overall. I'm going to write this as the degree of the top is less than the degree of the bottom. In that case, we have a horizontal asymptote. So let me abbreviate it that way, of y equals 0. Where we immediately do have a horizontal asymptote of y equals 0. If the degree of the top is actually bigger than the degree of the bottom, in that case, we're in a situation like part C. We divided by the degree of the bottom. Remember, the degree is the highest power. The degree here is actually 1 because the highest power of x is 1. I guess I probably should have said that a little bit earlier. But the point was, once we divided by that x, we didn't have enough to cancel out the x's on top from going to infinity or minus infinity. And so we're going to end up with stuff on the bottom that's going to a finite number, and stuff on the top that's going to be going to some version of infinity. In other words, we do not have a horizontal asymptote. We do not end up with a limit that's finite. We end up with infinity or minus infinity overall. The case that we are left with, though, is when the degrees are actually equal to each other. This is actually similar to our part B. In part B, our degrees on top and bottom are 1. The highest power of x was a 1. And so when we divide it by x, we end up having a term on top that had no x's in it, and a term on bottom that had no x's in it. And so we end up with a non-zero finite number as our limit. And notice that which terms actually survive. The term on top that survived was this negative 5, because our biggest term was negative 5x. That was the biggest power of x. On the bottom, the 2x had the highest power of x, and so we were left with the 2. We call the negative 5 and the 2 here the leading coefficients of those polynomials. Remember, the leading term is the term that has the highest power of x, and the leading coefficient is what's the coefficient of that term. So in the case where we do have equal degrees, we have a horizontal asymptote of y equals a over b, where a and b are the leading coefficients of p and q. Note that in this particular case, when we are talking about rational functions, it turns out, and we can prove this, that this will always be an asymptote for both infinity and negative infinity. The limit on either side will always end up being the same thing. That is not always the case for any general function, but it is actually the case for rational functions. We won't see any functions that are defined for the entire real line that have different asymptotes on the different sides. We'll actually see something like that in the next chapter, but we don't have any examples right now. Specifically, what we'll be seeing in the next chapter is the function e to the x, or exponential functions, if we want to put it that way. Those actually will have different behavior on positive infinity versus negative infinity. But rational functions always have the same behavior, meaning that they go to the same number on either side, if they do have an asymptote at all. So actually, let's see these rules in action. That's what I want to say. We're going to look at problem 30. We have a function here. It's 5x squared plus 1 over 10x cubed minus 3x squared plus 7. Now we could actually try to take the limit as x goes to infinity, and maybe use one of those same tricks that we used in problem 44. But we don't really need to. This is a rational function. We look at the degree of the top. It's equal to 2, because the biggest power of x was x squared. And the degree of the bottom, because the biggest power of x on the bottom is x cubed, we have a degree of 3. Since 3 is bigger than 2, that just immediately says that we have a horizontal asymptote of y equals 0. In fact, we already know that it's going to go to, this function goes to 0 on both sides. As x goes to infinity, we go to 0. As x goes to minus infinity, we also go to 0. There's nothing more we need to say. If we go to problem 34, here we have another function. We have x cubed minus 2x squared plus 3x plus 1 divided by x squared minus 3x plus 2. So it looks like there's a lot of stuff going on in here, but all we need to really worry about is what are the degrees. The degree of the top. What is the biggest power of x up here? It's an x cubed, so we have a 3. The degree of the bottom. This time, our biggest power of x is an x squared, so we have a 2. This time, 2 is actually less than 3. The degree of the top is bigger. And so that immediately says that there is no horizontal asymptote. And again, that's all we have to say. We don't have to worry about these other terms. The smaller terms really don't play a role at infinity. Essentially what's happening here is that the biggest term is kind of dominating anything else the other terms can do. This x cubed is so much bigger than all these other terms that what these are doing is not as important. It's the x cubed is by far the most important term on top. And on bottom, by far the most important term is x squared. And the x cubed is going to infinity faster than the x squared is. And so it's just not going to let it approach a finite number. 35, we have another rational function. Fortunately, this time it's not actually written as a polynomial over a polynomial. We have a polynomial over a polynomial, but then we also have another polynomial over another polynomial. This is technically still a rational function because we could combine the fractions, but it's actually kind of unnecessary here. If we want to know whether or not this has a horizontal asymptote, we can just ask ourselves, what would be the limit at infinity? We can think about what would be the limit of this fraction at infinity versus what is the limit of this fraction at infinity. Now, in this first fraction, we have a degree of 1 on top and a degree of 1 on the bottom. Those are equal to each other. And so, when we actually look at the limit as x goes to infinity of the top, of this first fraction, all we need to do is look at our leading coefficient. The leading coefficient of the top is 2. Leading coefficient of the bottom is 1. Remember, there's a hidden 1 in front of the x here. So the limit of this first fraction at infinity is 2. We can do the same thing for 3x over x plus 1. Remember here, we have degrees of 1 on top and bottom, so we expect to get some sublimit here. The leading coefficient of the top is a 3. The leading coefficient of the bottom is 1. And so that limit is 3. That means that the limit of these two together, if we just add these two fractions together, we're going to add their limits together. Basically, here we have a horizontal asymptote of y equals 5, just because 5 is 2 plus 3. As one final example, let's look at problem 48. Here they give us a function f of x is equal to the square root of x over x squared plus 3. Now they're actually asking us to evaluate the limit at infinity, but let's think of this in terms of horizontal asymptotes. Notice that the square root of x doesn't exist when x is negative. So this function doesn't even exist on the negative side. If it has an asymptote, horizontal asymptote at all, we're only talking about a limit off to positive infinity. And so really, what we're going to be doing here is exactly what they're asking for anyways. We're asking what is the limit as x goes to infinity of this function. We can't immediately use our rules for rational functions. This is no longer a rational function because we don't have a polynomial on top and bottom. So we're going to have to think about this a little bit more. But the tricks that we used in problem 44 actually are still true. We can think about what is the biggest power of x on top and bottom. It's actually still x squared in this case. We can remember square root of x is really just x to the 1/2 power. We can even write it that way, because now we're comparing the powers of x. I'm going to divide the top by 1 over x squared, multiply by 1 over x squared is the same thing as divided by x squared. Same thing on the bottom. On the top, remember, x to the 1/2 power divided by x squared, we subtract our exponents. 1/2 minus 2 is a negative 3/2. So our power of x on top is a negative 3/2. On the bottom, the x squared, we divide by x squared again, is a 1. And then we're left with a 3 over x squared for the other term. And the point here is once we take the limit as x goes to infinity, of course the 1 stays a 1. The 3 over x squared, we've already seen that kind of thing change to a 0. What is x to the negative 3/2? Where does that go? Well, our power here is a negative. That means x to a negative power ends up going to 0 as x goes to infinity. That was one of our rules back here. So if r is negative 3/2, then r is a negative, and our limit is a 0. So this top goes to 0 as well. So 0 over 1 is 0. this limit is in fact 0. Essentially what we're comparing our powers of x still. The power of x on the bottom is bigger. Our biggest power of x on the bottom is bigger than the biggest power of x on the top. 2 is bigger than 1/2. And so our rule for our rational functions is still kind of holding true, even if we're not dealing with a rational function. This is basically saying that our power on the top, or sorry, power on the bottom is bigger than the power on the top, which means that we end up having that horizontal asymptote of 0. Of course, in this particular case, it's only on one side. It's only on the positive side. But it really just comes down to that. We're still only really comparing what are the powers that we're dealing with. Now we'll see a few examples that are kind of like this in the next section as well, when we actually go ahead and actually start graphing stuff. So we'll investigate a few other possible situations, but I'm going to leave that to the next set of videos. So I'm going to leave this here. We know how to deal with both types of asymptotes now, and so we're ready to start graphing stuff. So I'll see you then.